Okay, you guys can see my screen as well?
Yes, sir.
This is going to be a problem. Okay, so welcome everyone. Good evening. My name is Ashwant, and I'll be your PMR of TA for this course, Drug Delivery Principles and Engineering. This is week one. We'll try to have this session every week, and basically in an attempt to look at various questions from previous year's assignments and try to solve them and give you guys an idea as to what kind of questions that usually come out of this course and also clear any doubts that you guys might have. So, uh, have you guys had the opportunity to go through the week one lessons? Like, where are you guys in terms of lessons? Like, have you finished week one lessons or are you still going through them? Hello.
Have completed the week one, sir.
Okay, you've finished week one lessons. Okay, great. Okay, so I'll have to figure out how to do this automatically the next time. But yeah, okay. So let's go ahead and get started. Let's look at various questions that have been asked in previous year's assignments. And yeah, I'm already recording this session. The video will be uploaded to YouTube. Yeah, if you guys want a link, I can share you the link as well. So yeah, it's being recorded. Okay, okay, so okay. Okay, so let's go ahead and get started. You guys have already heard of what a prodrug is if you finish the week one lesson. So uh, if we were to look at this question, so the question basically asks you what a prodrug can be. So does anyone want to volunteer what the answers could be? What do you think a prodrug is? Is it a prophylactic drug? So
Sir,
yeah.
an inactive drug that
An
is
inactive
transferred
drug.
in the body to an active metabolite.
Okay, so an inactive drug that is transformed in the body to an active metabolite. Yeah. Okay, that's a good
Sir,
answer. That's yeah. Go ahead.
Sir, drug conjugated to enzyme delayed. I think second option, sir.
Let's just see. Yes, probably can see the answer, but that's okay. Yeah. Drug conjugated to enzymes cleavable by biological systems. Yes, you are correct. So both of the answers are correct. So a drug that is conjugated to enzymes that's cleavable by biological systems is also a prodrug. And obviously, the drug that is an active drug that is transformed in the body to an active metabolite is the uh, ideological definition of a prodrug. So yeah, both of you are correct. Okay, I'm not going to accept anyone trying to join the meeting from now on because it's going to be a problem, I guess. But yeah, okay. So let's look at the next question. Which of the following drugs are absorbed in the greatest amount? So you guys must have read about bioavailability and what the area under the curve is and all those things, right? So if you guys look at the
sir,
question, yeah,
sir, I just joined, sir. I mean, I have joined the course only now.
okay. Oh, I see. Oh, okay. So okay, then let me assume that none of you guys have gone through the week one lectures. Okay, so if you were given a question like this, so which of the following drugs are absorbed in the greatest amount? So every drug has this thing called its bioavailability. So to briefly recap, bioavailability is basically if you were to give a drug through intravenous route and a different and a different route. So, what basically is the area under the curve of the drug that the total drug that is present in the plasma through the two routes. So if you were to say, let's take an example. So let's take paracetamol as an example. You can take paracetamol tablet, right? So if you take the tablet orally, there is some amount of drug that is going to be absorbed in your body. And whereas if you develop very high fever and you go to the hospital, they usually give it through intravenous route. So they put this saline and they put the drug in the saline container. So that's an intravenous route delivery. So if it's given intravenously, it will readily reach your plasma, blood plasma. So it has 100% bioavailability. But if you take it orally, it first has to go through your digestive system, it has to pass through your liver metabolism, intestines, and all those things, and then eventually it will end up in the bloodstream. So it's going to take some time, and in the process, the drug is either eliminated or it's destroyed by your body. So uh, obviously the drug that's going to be finally there in your plasma through oral route is going to be much less than what is given through intravenous route, right? So uh, basically bioavailability is the ratio between those two. So in the first example, if I were to say bioavailability of 0.7, it means 70% of the drug is going to be uh, inside your plasma. So it's going to end up in your plasma. So with that in mind, so let's try to answer this question. So which of the following drugs are absorbed in the greatest amount? So the first option is 100 mg of drug that's administered, and doesn't matter what route. It's because we know the bioavailability, right? So the bioavailability is 0.7. Okay, a lot of people. Yeah. So the bioavailability is 0.7. So 70% of the total drug that is administered is going to end up in your blood plasma. It's going to be absorbed by your body. So 70% of 100 mg is 70 mg, right? So in the same way, if you guys look at the other options, like which of the following drugs do you think is going to be absorbed in the greatest amount? Is the question clear?
Sir,
80
ATMG
mg
drug
drug
administered
administered in
intravenously.
One at a
20 mg
one at a time. Yeah, go ahead.
80 mg drug administered intravenously,
Okay.
and second is the 20 mg given intravenous, because intravenous administration route of administration shows the 100% bioavailability.
Okay.
So these two answers should be correct.
Okay, so yeah, another person had another answer, I believe.
I
Only
guess it
first,
Sir,
is
only first
I
answer is correct, sir.
Sorry.
100 milligram of drug administered, bioavailability is zero point 0.7. This
Oh,
one is correct.
okay, okay.
the
Any
third
point?
option and the I would say the fifth option.
So,
20 mg are given intravenous is correct, I think.
okay, okay. Anyone else wants to guess?
sir, ATMG drug administered IV और सर सेकंड होगा 100 mg drug administered by availability 0.7.
Okay, okay.
Sir, I think we have to calculate the percentage because in some options they have given that bioavailability, they have mentioned 0.7, 0.5, and
correct.
the amount of drug is also different for all the options. So, according to the percentage, we have to calculate it first that how much is the mg
Okay, how would you calculate
amount
that?
of the drug. Like you said that 100 mg drug administered bioavailability, if it is 70%, so that according to that percentage, do you need to calculate that first?
Correct. Yeah, you are correct. So you need to look at the options in that way. You're absolutely correct in that. So if I take the first example, so 100 mg of drug is administered, bioavailability is 0.7, meaning 70% of the drug is going to get absorbed in the body. So you have to look at what 70% of the 100 mg drug is. So 70% of 100 mg is 70 mg, right? So 70 mg of drug is being absorbed by your body in the first case. Similarly, in the second case, if you look at it, so uh, zero point 0.5 is the bioavailability. So 50,
75.
yeah, it's 50% of the drug. And the third option, 0.4. So does anyone want to calculate?
It's 80.
That's
Oh,
80.
okay. So the fourth option,
Uh,
So fourth option, it will be 50.
50.
okay. So and the fifth option is
80.
80 mg that's administered intravenously. So remember, if you administer drug intravenously, it's directly accessible by your blood. Like, yeah. So if you administer a drug intravenously, it's directly accessible to your blood plasma, right? So if you administer 80 mg of drug intravenously, all the 80 mg is going to be taken up by your body. Correct?
Yes, sir.
Yeah. And the
Yes, sir.
next
Right.
option is something that administered
200 mg.
orally. So the problem with oral administration is that so what happens when you take a drug orally is it goes through something called the first pass metabolism. So it has to sort of bypass the liver and go outside and then merge with your bloodstream, right? So liver is a very strong metabolically active organ of the body. So it is not going to simply let a drug molecule pass through it unaffected. So it's going to metabolize the drug as much as it can. So obviously the total drug uh, amount that you consume is not going to ultimately end up in your bloodstream. So there's a lot of loss that happens orally, right? Okay. So, so if you look at all the options, it looks like in all the cases, the maximum amount of drug that your body can absorb seems to be 80 mg, right? So, what gives us 80 mg here? So,
The
200
third
mg.
option and the fifth option.
The third
Correct.
and the fifth.
Correct. So someone has said 20 mg of the drug that's administered intravenously. So you're correct in thinking that if you administer 20 mg of the drug intravenously, all 20 mg will go to the blood plasma. But in this case, it's not the greatest amount, unfortunately. So 80 mg is the greatest amount. Is that clear?
Yes, sir.
Yeah. Okay. Okay. So we'll move on to the next question. Before that, let me quickly admit people. So I think Google Meets does not have this auto admit feature. So I'll try to figure it out. But in any case, let's try to join before 7:05 because otherwise it becomes constant shuffling between the Chrome extension and this. Anyways, so which of the following equations depict a second order reaction? So have you guys had the opportunity to look at what first order reactions and second order reactions are?
Yeah, we have.
Yeah,
Yeah.
But the second one is the correct answer.
okay. So you're saying the second
Option
one
two.
is okay.
Option two.
Everyone
Second
agree?
option.
Everyone agrees?
Yes,
Yes,
Yep.
sir.
sir.
Okay. Yeah. So
Sir.
obviously, so I will not elaborate much on this. So do you know what the first option is?
That's a zero order reaction.
Zero order.
That's a
Perfect.
zero order.
Perfect. And the second option is obviously the second order reaction, and the third option,
First
That's a
order.
first order.
First order reaction.
First
correct.
order.
And the fourth option,
Fourth order, I guess.
not really. It's
Like,
also a first order reaction. So
Zero order, sir.
no, so it's a first order reaction. So K is any constant that you define, right? So 4 times K is also a constant, so it doesn't matter. So it's still a first order reaction. Yeah. Okay. So, okay, let's go on to the next question. Which one of the following will have ease of permeating through cell membranes? So we have different drugs
It will
here.
be the second option, right?
So you're saying drug with higher partition coefficient and a drug that is not polar is going to have uh, will have the highest ease of permeating through cell membrane, right?
Yeah, yeah.
Okay. Does anyone have any other answer?
Non-polar and high partition coefficient.
Okay. Yeah. So same as the previous
Yeah,
person.
yeah.
Okay. Yeah, you guys are correct. Obviously, so if you look at the structure of the cell membrane, it's made of lipids, right? Mostly lipids. So so lipids really are very hydrophobic in nature, so they do not readily allow very highly polar substances to pass through them. So obviously, the molecule should be very non-polar to be able to pass through the lipid bilayer. And by higher partition coefficient, if anyone wants to try to answer.
Higher
So
the partition coefficient, more it is lipid soluble.
perfect, correct.
Is
So
directly proportional to the lipid solubility of drug to pass through the lipid bilayer membrane of cell.
perfect,
So it should be directly proportional. So
correct,
the
correct,
greater partition coefficient then can be greater amount of a drug can be passed to the
correct,
lipid bilayer.
correct. 100% correct. So partition coefficient for those of us who do not know. So it's basically the solubility or the dissolution of the drug in oil phase over aqueous phase, right? So lipids are oily in nature, so to speak. So, if a drug has a very higher partition coefficient, it's going to be much more soluble in lipids. So, it's going to readily transverse the bilipid membrane that's present in cells. Okay. Okay, so bioavailability by definition is defined as which of the following? So, for those of us who have just joined the course, so this might be a little bit of a definition, so to speak. So it might be a little bit challenging to answer, but those of us who have already attended, so which of the following formulae do you think is relating to bioavailability of a drug?
Route by
The
IV.
first one.
First option.
First option, route by IV.
Everyone agrees?
Yeah.
Yes, sir.
Yeah,
Yes.
yeah,
Yes.
absolutely correct. So bioavailability again is just to reiterate. So remember, intravenous, if you deliver a drug intravenously, it has 100% bioavailability. So if you want to calculate the bioavailability of a drug that's given through a different route, so you have to do AUC of a route by AUC of IV. So what is this AUC?
This is
Area
area
under the curve.
under
Area
curve.
under curve.
Area
Okay,
under
Area
so
curve.
under curve.
area under the curve.
For
Area under curve.
bioavailability.
What curve are we talking about here?
Bioavailability.
By
Yeah, so the plasma concentration of the drug.
Yes.
Yes.
How much of the drug is present in your bloodstream of the plasma, right? So that's the area under the curve. Okay.
yes,
So why is it area under the curve? Why is it not a constant answer? Like so why is it not like okay 10 mg of drug is present in the plasma? Why is it an area under the curve?
It depends
Because
upon time the drug is getting eliminated also.
Perfect.
So the
Yeah.
amount will
the
decrease.
drug concentration in the plasma will vary at different points of time. So
Correct. So obviously, elimination is a big part of it, but it also takes time to build up the drug in the blood plasma, right? So uh, during the initial times when you first take the drug, it will take some time to for the drug to start building up its concentration in the plasma. So that's why it's an area under the curve. Okay. Okay. Let's look at the next question. So, the VD of a drug is known to be 30 liters. VD, for those of us who do not know, is the apparent volume of distribution. So, given the VD of a drug is 30 liters, how do you expect the drug to distribute in the body? Does anyone want to answer the question?
It will distribute in the total body water, right? Because
Correct.
the body water volume is
Total
also
body
30
water,
liters.
yeah.
Body water.
Correct. Correct. So why is it?
Because the total volume of water in the body is 30 liters.
Yeah, perfect. For an average adult,
Yeah, and the
it's
blood will be included in that
yeah,
too.
perfect. Uh, yeah, so it's distributed in the total body water of an average adult. Okay, so let's look at a couple of numerical problems. I'm not including too many because from the previous year's assignments, because you guys have this year's assignments as well. But let's look at a couple. So the median lethal dose of a drug is given to be 320 micrograms per kg, and its median effective dose is given to be 80 micrograms per kg. Given this information, what do you guys think is going to be the therapeutic index of the drug?
It'll be 4.
0.25.
Okay. Any other answers?
Is it not 4?
So it is four. So the therapeutic index of a drug is determined as the median lethal dose of a drug over the median effective dose. So not the other way around. So it's median lethal dose of the drug divided by the median effective dose. So it's going to be four. I guess you've taken it the other way where median effective dose over median lethal dose, but yeah, so it's LD50 by ED50.
Yeah.
Yeah. Okay. 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 So we'll move on to the next numerical. So a polymer is made of the following compositions. Let me just type this person. Okay. So a polymer is made of the following
Hello, sir.
composition. Yeah.
Sir, can you repeat previous question? I'm not understanding how to calculate, sir.
Sure, sure. So therapeutic index of a drug is a property of the drug. So the therapeutic index of a drug is defined as the median lethal dose of a drug divided by the median effective dose of the drug. So if the median lethal so if a drug was given in very high amounts, it's going to kill a person, right? So basically, what the median lethal dose tells you is if you give 320 micrograms per kg of this drug to 100 individuals, 50 of them will die. And if you give 80 micrograms per kg of this particular drug to 100 people, 50 of them will get cured of the disease. Is that making sense?
Yes, sir.
Yeah, so, given this information, people have defined this arbitrary term called therapeutic index. So, the therapeutic index of a drug is basically used to relatively compare the clinical efficiency as well as the toxicity of different drugs. So, let's say for drug A, the therapeutic index is 1, and let's say for drug B, the therapeutic index is 10. Which of the drugs do you think is given in higher amounts? Anyone?
Uh, could
Sir,
you
could you
please repeat
repeat
that?
again?
Yeah. So let's say I have two drugs, drug A, drug B. Drug A's therapeutic index is 1. Drug B's therapeutic index is 10. Which of the two drugs I can give in higher amounts?
Drug A,
Drug
I
B.
guess.
Drug
Drug A.
B
Drug
because
B.
Drug A.
Yes, yes, let's be.
because there's a
Drug
wide
B.
range in the therapeutic index.
When there will be
So
the
the
wide range between the ED and TD, sir?
Sorry, could you repeat that?
Drug B.
Drug B, sir.
Yeah, there was a question. Okay, so let's look at it. So therapeutic index, as I said, is defined as the le median lethal dose of a drug over the median effective dose, right? So if the therapeutic index of a drug is to be 1, it essentially means the median lethal dose and the median effective dose of the drug are the same. So if you want to cure a disease, but do not want to kill the patient, you cannot do that. You can only do that in 50% of the people. So let's say like 100 micrograms of the drug is required to cure a disease. So that's the median effective dose. So 50% of the people, if 100 people were to take the drug, 50 people will get cured if you give 100 micrograms. But if you give 100 micrograms, you're also going to kill 50 people, right? So you cannot give 100 micrograms. Make sense?
Yeah, that
Yes.
makes sense.
Yeah, so
Yes, sir.
now let's look at drug B. Drug B has a therapeutic index of 10, which means the median lethal dose is much higher than the median effective dose. So you can give a lot of drug before you start killing people, so to speak. Any questions?
Yeah. No, sir.
Okay, so with that, that's what therapeutic index is used for, to relatively sort of compare drugs and how much of a dose to give. So now let's get back to this question. So what is the index of a drug if the median lethal dose and the median effective dose are given? So all you have to do is basically take the ratio of the median lethal dose over the median effective dose. So uh, if I were to take the ratio of 320 over 80, it gives us 4. That's the therapeutic index of the drug. The person who has asked to repeat the question, is this clear now, or should I go over it once again? Oh my. Hello.
Yes, sir. Completed, sir.
Okay, you understood?
Yes, sir.
Great. Okay. So let's look at the next question. A polymer is made of the following composition. So there's this polymer that's formed by mixing two different polymers, right? So 6 moles of polymer A is mixed with 11 moles of polymer B, and the molecular weight of polymer A is 30,000 Daltons, and the molecular weight of polymer B is 55,000 Daltons. So, given this information, can you guys tell me how one would go about calculating the polydispersity index of the final polymer?
the uh,
Average
this
weight of the polymers divided by total
uh,
number of
uh,
moles.
number average molecular weight by weight average.
Okay. Okay. So, how do you calculate the number average molecular weight of the polymer?
It's the number of moles into molecular weight by total number of addition of three.
Okay, okay. So actually, the final polydispersity index is the weight average by the number average. So it's not number average by weight average; it's weight average by number average. Because weight average is always going to be greater than or equal to the number average of the polymer. But let's look at how one would go about solving this problem. So, yeah, as someone was suggesting, so you have 6 moles of polymer A of molecular weight 30,000 and 11 moles of molecular weight 55,000 polymer B. So 6 times 6 times 30,000 plus 11 times 55,000 over 6 plus 11. That will give you the number average of the uh, final polymer mixture. And to calculate the weight average, all you have to do is the number of moles times the molecular weight squared over the number of moles times molecular weights of the individual polymers. So if you do that, you get these values, and uh, so can anyone tell me what happens when so here the number average molecular weight is given out to be around 46,000, and the weight average is given out to be around 48,000, right? So when you take the polydispersity index, it's molecular weight, average molecular weight of the polymer divided by the number average molecular weight of the polymer. So it gives us around 1.06. Can anyone tell me what happens when the situation is flipped? So when the weight average is so let's say when the number average is 48,900 something, and the weight average is 46,176, and the polydispersity index is less than 1. So what would happen in that case?
I'm not sure, but is it the case like it will be a monodisperse
Okay.
product or powder?
Not really. So if you have a polydispersity index of 1, then that would suggest it's more or less homogeneously dispersed. But so remember always that the weight average molecular weight of a polymer is going to be, no matter what, greater than or equal to the number average molecular weight of the polymer. So the polydispersity index range is always 1 or greater than 1. So the lower limit of a polydispersity index is 1. Well, I guess someone found that funny. Okay. Anyways, yeah. So any questions? Sorry, could not hear you properly. Hello. Vanessa, could you please repeat the question? I could not.
No, sir. Next.
Okay. Okay. So with that, I thought I'll just go over some of the questions that you guys have asked in the forums, and try to sort of answer these questions. So I've done this 4 or 5 days back, so I might have missed the most recent questions, but we'll go over these anyways. So the first question asks, since VD will be time dependent, the VD values of the 3 drugs are at what time? Okay. Let's get back to this question. I'll have to go back and check with what context he's asking to. So I don't think he's mentioned the context. So if you're around Ramesh Krishnan, so could you please tell me what context you're asking? Like what are these 3 drugs? Okay. So if you're around, please unmute yourself and ask me, like, give me more context as to what the 3 drugs are. But okay, let's move on to the before that. Let me. Okay, so the next question asks, if we use thermosets, it might be difficult for a person to install it in a patient because they are so rigid. The cut which would be required to install it would be bigger, but on the other hand, elastomers have this advantage of being flexible. Okay, so do you guys remember what thermosets and elastomers are?
Yes.
Okay. So if you guys remember, so thermosets are basically polymers that have that usually set with generally with temperature, and they're very rigid in there. So once they're set, they cannot be reshaped or remolten back to a native state, right? Whereas elastomers can be reshaped or restructured after they've set. So the question asks, like, so if you were to insert a thermoset in a patient, because they are so rigid, would that not require a bigger cut than elastomers? So making elastomers a much more flexible choice in bioengineering. Do you guys have any thoughts on this? Anyone?
Could you please explain it again? I didn't get it.
Okay, so a thermoset is basically a polymer that generally sets with temperature, but once it's set, it's very rigid. Like you cannot change its shape, or you cannot restructure it, or you cannot remelt it and reform it. So once it's formed, it's formed. Whereas elastomers, they are much more flexible in their nature, right? So once they are formed, you can twist and turn and reshape them, and you can even remelt them and sort of reform them. So given this, the person asks, so because thermosets are so rigid, when you want to insert a thermoset in a patient, will that not require a bigger cut than elastomers? So thereby making elastomers much more favored polymer to insert into the body.
But wouldn't the structural integrity be compromised if we used an elastomer?
Yeah. So yes, to an extent, yes. So okay. So now that you've said it, so you think structural integrity will be compromised if you're using an elastomer, right? So where do you think structural integrity would be an important aspect when you're bioengineering a body?
Somewhere where we're using biomaterials in the place of bones,
Perfect. So
fillings or whatever.
perfect. So thermosets are usually generally used in sort of bones or dental surgeries. So where the structural aspect of it becomes so important that you cannot really use elastomers, right? So that's where thermosets are generally used. And so so again, just to talk a little bit about requiring bigger cut. So the problem is like, so it depends on the application, right? So if an application demands a bigger cut, obviously you're going to have to cut the body in a much bigger way than you normally would. So the problem with elastomers is, so let's say I need to sort of hold two bones together. So like there's a bone fracture, and the bone has sort of come off. Now I want to inject a material that can hold the two bones together. I can use elastomers, but again, as someone has said, like it's compromising the structural integrity. So when you put weight on the bone, obviously it's going to shift a little bit. So it's because it's flexible, it's going to move. But if you use a thermoset, it's going to be rigid. It's going to be properly attached together, right? So yeah, to basically answer this question, it's application dependent, and thermosets are mostly used for bone and dental implants and such things, right? So obviously there you need the rigidity. So if it demands a bigger cut, so be it, but you can't compromise on the rigidity. So that's the answer. Anyways, let's go.
With regards to the same question,
Huh.
is there any application for elastomers in the in medical field as such?
Yeah, there are. So elastomers are commonly used for drug delivery. They're also used as drug. So for all these delayed release and sustained release and controlled release, they use elastomers quite a lot because of the nature of flexibility that they offer, and they do not impinge upon any structural elements in the body very too much, right? So if you want to implant something that's not in the bone, you're much more likely to use an elastomer because you don't need that rigidity there. So so let's say I want to place a subcutaneous implant. Let's say I have a drug. I want it to have a controlled release, and I want it to be placed subcutaneously in my body. What am I going to do? I'm not going to use a thermoset because there's something hard that's going to, like, whenever I do this, it's something hard that's there. And if I hit it against something, it's going to break much more easily, right? So elastomers offer much more greater advantage there.
Right, right. Okay.
Okay. Okay, so the next question asks, which drug will have the lowest solubility because the graph of tetracycline eventually goes up? Only chloromazine comes down, so will it have the lowest solubility? And this will be true at any pH. So I think they're referring to this graph. Let me read it. Which drug will have the lowest solubility because the graph of tetracycline eventually goes up. So they're saying this graph of tetracycline comes down, but it eventually goes up. So which will will tetracycline have the lowest solubility, or which will have the lowest solubility? And also, will it have the lowest solubility? Okay. To the person who asked the question, so this graph is basically comparing the solubility of these three drugs at different pHs, right? So if I were to take tetracycline, it's most likely going to be in a physiological pH inside your body, unless it goes into your stomach, where it has a very high solubility. But once it passes your stomach and goes into your intestine, obviously it has very high solubility here again. But once it enters your bloodstream, it's going to have very low solubility. So yeah, so it's not about the overall solubility of the drug. The drug is soluble at different levels and different pH. So you can use, like, you can make tetracycline 100% soluble with acidic pH, or 100% soluble with basic pH, but mediocrely soluble in physiologically relevant neutral pHs. So it's not the question of which drug has the highest solubility or the lowest solubility. It's that these drugs have different solubilities at different pHs, and basically we are looking at how. Uh, Basically, we want to understand the fact that different molecules have different solubilities at different pHs, and we want to see if we can explore that. Yeah, and
Sir,
the yeah.
sir, in tetracycline, can we say that it is having more than one pKa values? Like at lower pH also it is highly soluble, and at pH 12 or more than that it is soluble. It means it is getting ionized.
Correct.
So, like, will it have more pKa values?
Yeah, it will.
Okay, sir.
Yeah. Yeah, so let me go. And this will be true at any pH. Uh, yeah, so if the person is around, maybe they can jump in and try to sort of re-ask this question. But yeah, so this will not be true at any pH. So like different pH, different drugs have different solubilities. So if I were to look at pH 6, then tetracycline has the lowest solubility at that pH, right? So followed by indomethacin and followed by chlorpromazine. But if I were to instead look at pH 12, chlorpromazine has the lowest solubility, whereas tetracycline has somewhat medium level solubility, whereas indomethacin has the highest solubility. Yeah, so hopefully that answers your question. Okay, let me go back to this. Okay, I have a question about what is happening. What is the effect of polymer drug conjugates on stability or overall stability? Okay. So this person asks what so he has linked to the beginning of the video, but what is the effect of polymer drug conjugates on the stability or overall stability? Okay, so generally speaking, polymer drug conjugates have improved stability compared to the drug alone. So again, it depends on what you define as stability, right? So is it stability against reactive oxygen species at a given pH? Is it stable? Is it thermal stability of temperature sensitivity and temperature resistance, or so on and so forth? So it depends on what you define as the stability. But if you were to talk about stability in terms of pharmacokinetics, where the drug is more stable in terms of it not getting eliminated very quickly, then yeah, that's why we do polymer drug conjugates. So to improve the half-life of the drug and to sort of various other reasons, but one of the reasons is obviously to make the drug, so to speak, more stable. Yeah. So does that? I don't know if the person is around, but if you have further points you need to clarify with regards to this, feel free to ask. The same person asks, can you give me insights about controlled release, delayed release, immediate release, sustained release, and prolonged release? Okay, so so controlled release is basically so you have a drug. The ultimate aim of drug delivery is to sort of strike a balance between achieving very good drug half-life and also very good therapeutic value of the drug, right? So controlled release is basically wherein, let's say you take this drug and you engineer it in such a way that it's getting released in the body under specific cues, right? So it could be either temperature, pH, protein, a specific protein is present, or a specific cell is present, even, or a specific tissue is present, or a specific hormone is whatever. So that's controlled release, where you're controlling the release of the drug based on some external factor. Delayed release is basically the release of the drug, as the name suggests, is getting delayed. So it's having a much more uh, prolonged release, as opposed to when you take a tablet and it's just there, or when you put it in your veins, it's just there. So obviously you won't extend the half life, so you do this delayed release, and these can be achieved with biomaterials. So in future classes, you'll study about various systems in which people have sort of achieved higher half lives for drugs based on different release profiles. And yeah, immediate release is again, like, let's say you were to take a drug through intravenous route, that's immediate release. So the drug is going to get immediately available for your body to use. And sustained release is, so these terms are used a little interchangeably. Sustained release or prolonged release is basically you have a very long course of time during which the drug is released. So these can be achieved by using different types of polymers, like PLGA, for example, which is FDA approved and much commonly used for these uh, drug release platforms. So if you were to load a drug in PLGA microcarrier, it's going to get very slowly released. So it's going to have a very sustained release, which is going to sort of extend the therapeutic window of your drug and reduce the amount of doses that you need to take for So to give you an example, if you were to get a disease, so let's say if you were to get a fever, you go to a hospital and the doctor asks you to take a paracetamol, and he'll ask you to take a paracetamol once in the morning, once in the afternoon, and once in the evening. So that's three doses, right? So you in an ideal world you want to avoid that, because like a lot of people will forget taking third dose, or they don't have time to take the third dose, and it doesn't matter much in case of paracetamol, but if it were antibiotics, then that would sort of cause this rise of antibiotic resistance. So you want to limit the number of doses that people will take so that it's much more patient compliant. So instead of taking three doses, if you were to just take one dose in the morning, that would be a much more ideal world, right? And instead of taking one dose, if you were to take one dose every 6 months, just imagine that, like you every 6 months you go to a hospital, the doctor will give you a dose, and that's it. You're good to go for the next 6 months. So that's why people sort of look at sustained release and prolonged release as a mode to both improve the half-life of the drug, achieve a very wide range of therapeutic value, therapeutic window, so that there's very high degree of patient compliance. Okay. So if you guys have any other questions, please feel free to shoot at me, and like you can always reach out to me through email. But if you guys have any questions, you can ask me as well.
Sir,
I have
can you
one question.
say class, general class when start, sir?
Sorry.
Sir, can you say general class when start?
So the classes, the lectures are being like the lectures are being made available to access every week. So week one has already started, and the assignments are due sometime this month, I believe. So 10th or something. I'm not sure. I'm not quite sure,
Yes,
but
sir, 10.
Yes,
yeah,
sir, 10th of August.
yeah, 10th of August, the assignment is due. So and you guys will have your live session very soon. So I think 18th August is your live session. So you'll get an official intimation, but Rachit will take a live session for you guys quite soon. So, but the classes have so the course in NPTEL works in this way, right? So you have these lectures that are being released on a weekly basis. The expectation is that you go through the lectures and you try to learn and try to sort of finish your assignments. And once a month, you'll have live sessions with Rachit, and every week you'll have a live session with me, where we'll sort of look at previous year's assignments, and we'll also try to answer some of your guys' questions. Make sense?
Where do we access the assignments?
So the assignment should be in the portal itself. So if you click on week one, once you finish all the lectures, like the last tab should be week one assignment. Maybe someone who has finished the assignment can guide you. Has anyone tried to finish the assignment? Oh, I think Suleiman is here.
Yes, sir.
Yes, sir.
Yeah. So is it under the week one tab?
Yes, sir. After we complete the lessons, there's a tab.
Okay. Yeah. So if you check the week one tab, it should be there. Hey Suleiman, we've just answered a couple of questions you've had. So basically, to recap, so what is the effect of polymer drug conjugates on stability? So it depends on your definition of stability. If you're talking about the improvement of the pharmacokinetics of the drug, definitely polymer drug conjugates improve the stability, improve the pharmacokinetics of the drug. And the next question is a much more detailed one, where you will begin to learn about these delayed release mechanisms and sustained release mechanisms and controlled release mechanisms eventually. But controlled release is where you release the drug under specific environmental cues. Delayed release is where you have the drug that's being released after a given amount of time. Immediate release, as the name suggests, the drug immediately comes out. Sustained release and prolonged release are where the drugs are released for very extended periods of time.
So I have a doubt.
Yeah.
In the recent years, I have a vague knowledge as to how nanomaterials are being incorporated in drug delivery systems.
Mm-hmm.
Uh, how's the bioavailability and all the other aspects uh, enhanced or in a way different than the normal ways of drug delivery systems that are
Okay.
current?
Okay. Great question. So okay, let me start. Okay, so let me take an example. So you have a drug whose bioavailability, if you take it orally, is given as, let's say, 0.2. Uh, 20% of the drug is going to end up in your plasma. Now, so the ambition with nanoparticle based carriers is that, so you want to bypass this first pass effect, right? So I guess the question comes like, is there a problem with the current system? So only 20% of the drug is getting into your plasma. So does that mean that you'll have to take much more frequent doses? In which case, then obviously there's a problem. So if you were to engineer a nanomaterial based solution to that problem, what you want to look at is, obviously you want to make sure that you reduce the frequency of this doses, right? So there are a couple of ways to do it. One is, so when you take a drug orally, it can have very drastic side effects. So it's not being slowly released. It's being released all of a sudden. So if it has any side effects, they're going to be pronounced. So if you were to design a system where the drug is sort of slowly released, then that's going to be much more beneficial, right? So the side effects will be much less. And the other aspect is the bioavailability. So whether you want to increase the bioavailability or decrease the bioavailability depends on application to application. So for example, if I were to sort of take a drug, so if I were to if I was finding that 20% of bioavailability is sufficient for me to get a therapeutic effect, then I need not really worry about too much about increasing the bioavailability, right? So that's one thing. But if this 20% is not enough, and that's why you have to take multiple tablets at a frequent dose to sort of build up the concentration, then obviously you want to improve the bioavailability. So you can think about changing the route of administration of these nanoparticles. So you can, instead of taking orally the nanoparticles, once you've engineered them, you can sort of make a depot in your arm. So you can subcutaneously put an implant, and there's a depot of the drug which will slowly release into your bloodstream with an improved bioavailability. Uh, Otherwise, you can just give them orally. So basically it's application based.
Okay, but as the general trends, I have not had a study about it, but if you know about it, how do the general trends of usage of nanomaterials or nanoparticles have deemed to be better when it comes to the normal drug delivery systems?
Okay, so you're asking what's the benefit of nanoparticles?
Right, how specifically do they benefit?
Okay.
Uh,
Okay, so let me give you an example then. So, do you know about this disease called osteoarthritis?
no.
Okay, so osteoarthritis is basically, so when you have a knee injury, or when you grow old, the cartilage in you, so your knee is like this, right? So it has this flexible movement that's going on. This movement is enabled by a cartilage. So when this cartilage erodes, these bones are going to rub together. It will cause a lot of inflammation. There's a lot of cellular physiological changes and so on and so forth, right? It's a very painful disease. So what happens is, people have found out that there's this drug molecule called rapamycin. So I don't know how many guys have heard about this rapamycin. So if you guys know a little bit of cellular physiology, so there is this protein called mTOR in mammalian cells, mammalian target for rapamycin. So rapamycin can directly act on mTOR, and it can sort of it cannot completely cure osteoarthritis, but it can reduce the inflammation and increase autophagy and sort of elevate the symptoms of osteoarthritis. But what people have also found out is that this rapamycin is very toxic to humans. Like you can't just take tablets of it and expect to be fine. Like it has a lot of side effects and it's very toxic to humans. So people do not generally prescribe rapamycin for people to consume. So how do you address this? So people have started developing various nanoparticle based, polymer based nanoparticle and polymer based drug delivery systems where you can sort of inject these nanoparticles into your knee, and you can sort of directly release the rapamycin into your knee itself so that it does not have as much of a systemic toxicity. So that's just one specific example of how nanoparticles are sort of helping us develop better drug delivery systems. So what are you going to do in case of a drug you know is going to cure a disease, but you cannot take it because it's very toxic to your body? So how are you going to achieve a balance between those two? So that's where nanoparticles can come in and sort of give you the flexibility to control the release, guide the release, and really fine tune how much of it is being released and all those things so that it remains less toxic to the system as a whole. And there are several examples. So if you just go to PubMed and look at various, just use key phrases like nanoparticle based drug delivery, and you will stumble upon various n number of articles that talk about the different problems with a given current drug delivery system and how nanoparticles can be a better uh, uh, platform for the delivery of the drug.
Okay, sure. Thanks.
Yeah. Okay, there are some questions in
So,
chat. Yeah.
what would be the ideal range of polydispersity index?
So it depends on your application, but ideally you want to keep it as close to one as possible. So you want the two polymers to sort of mix well together, no?
Okay, sir.
Yeah. But yeah, you want to keep it as close to one as you possibly can. Okay, let me look at chat. Yes, this video will be on YouTube. I'll share a link. Someone says I am present, sir. I'm not taking attendance. Mm, Can you repeat if it's less than one? Okay, so I guess they're talking about polydispersity index. Polydispersity index cannot be less than one. The minimum value for polydispersity index is one. It's greater than one, but the minimum value it can be is one. Okay, but reach index. Sustained release or prolonged release have side effects. So they do. So the idea is that you reduce the total number of side effects that are present, right? So if I were to take a drug which has like 10 side effects, and three of these 10 side effects are because of the concentration of the drug that I'm taking, you want to eliminate those three side effects through sustained or prolonged release. Yeah. So they generally the goal is to have the same amount of side effects or way less side effects than what's normally taken. And generally, people observe that sustained release or prolonged release drugs have lesser side effects compared to normal drugs. Okay. Regarding polydispersity index, can you clarify regarding its range? If polydispersity, uh, doesn't it mean the system is more monodispersive? It's synthetic. Okay. So it the system cannot so okay so polydispersity index cannot be less than 1, mostly because the weight average molecular weight of a polymer is always going to be greater than the number average of the number average molecular weight of the polymer. And uh, doesn't it mean the system is more monodisperse if it's synthetic? If you are around, can you please what do you mean? All polymers are, or like if you're talking about a mixture of polymers, it's generally synthetic, right? So
Hello,
yeah,
can you hear me?
yeah, I can hear you.
Yeah, so I remember when you were using particle size analyzer, so in that, if the PDI was less than one, the system was more monodisperse in nature. But now I'm getting confused between the instrumentation and the formula because as per
So
formula it should be one, but
correct. So
yeah.
if the system is if the system is more monodisperse, it means like you haven't created a new polymer, right? Like so, if you take polymer A and polymer B, and you want to create polymer C, uh, ideally you want polymer A and polymer B to be present in polymer C. If you have a polydispersity index of less than 1, it means like uh, so the monodispersity of A, the monodispersity of B, together the polydispersity of C, right? So if you have a polydispersity of C that's less than 1, it means like you haven't really created C. It's more likely,
Okay, that clarifies it.
yeah.
But then I remember like during a practical work, like it was like point 0.7, but it was considered bad. So they wanted a period that's less than point 0.3. That would suggest that it's even more non-dispersed in nature.
Okay, I'm not really sure. Let so maybe they're talking about monodispersity index, but let me check and get back to you on this. I'll get back to you on, next week. Okay. So could you explain the very first question? Okay. The very first question is basically what a prodrug is. Yeah, a prodrug is basically a drug that you take, which
Sorry to interrupt.
yeah.
Is it okay if some of us leave
Yeah, yeah, yeah.
if it isn't anything?
Yeah, sure.
Okay, okay,
Feel free
thank you.
to leave. Yeah. Hopefully, I'll see you guys next week. Thank you for joining.
So where can I get this recorded session?
I'll post it on YouTube. I'll share a link with you guys.
Sir,
Thank you,
is
sir.
it possible to create one WhatsApp group? Actually, when we are going to do the assignments, there are few questions, actually, answers are very close. So at least we can discuss there.
Okay. I'm not sure about the ethicality of that. So I'm also your so I'm also your TA for the normal course. So let me think about this. You want to create a WhatsApp group where you can discuss questions. Yeah.
Yes, sir, at least for the assignment part, because since they have released for the second week also, so
Okay.
there are many questions, the answers are very close. So
Okay.
maybe we can discuss little bit over there and then we can decide about the answers. Because if it is for the certification course, those who are planning for the certificate course,
Okay.
so assignment scoring and everything will be very easy for us.
Okay. I can't tell you guys. I mean, that's up to you guys. If you want to create a WhatsApp group and discuss questions, I can't stop you, right? So, feel like up to you guys. But yeah,
Okay.
yeah. Okay, so basically the first question is what a prodrug is. A prodrug is basically something that you take. So it's a drug molecule that you take, but the drug molecule does not directly have any effect in your biological system. So it's designed in such a way that once you take it, your body can make it work. So your body metabolizes the prodrug and it will make the active drug. So that's what a prodrug is. So it's basically either a drug that's conjugated to enzymes that's cleavable by the biological systems or an inactive drug that is transformed in the body to an active metabolite. Okay. Yeah. Okay. Where to refer this? Yeah, again, I'll let you guys know. So we can, okay. So can we create a regular discussion? So the discussion forums are active in the NPTEL website. Uh, Feel free to discuss there. If you guys want to create a WhatsApp group amongst yourselves, feel free to do that. We will have weekly sessions. So if you guys have any questions, bring your questions. If I'm not able to answer them right away, I'll definitely look at them and try to answer as many as I can in the coming sessions as well. So yeah. Mm, clearance clearance formula. So I'm not sure what clearance formula. So it depends on the order of elimination. If it's a zero order elimination, first order elimination, or second order elimination, right? So they all have different formulae. A drug A is injected into a patient. The rate of elimination of A is 25 grams per minute, and its plasma concentration. What is the rate? I'm not going to answer assignment questions, guys. So maybe we can take a look at the assignment questions like once the deadline has passed. If you guys think that will be helpful for you. Rate of elimination divided by okay. So then why not take the activated drug instead of a prodrug? Good question. So sometimes the activated drug is very toxic. Like I was saying, rapamycin is very toxic to humans, right? So you don't want to take activated drug in that case. And also, people recently have been looking at forming these drug depots of prodrug. So they'll just inject like uh, a bunch of the drug into your body, and like your body will slowly start to make the drug itself, like instead of so let's say if I want to inject 10 mg of the drug, it's going to kill the patient, but I can inject 10 mg of the prodrug, which your body can convert it to 10 mg of the drug over a period of time, and the patient will be fine. So that's the benefit of one of the benefits of prodrug. Can we have more practice questions posted? Sure. This time I only looked at assignment questions, but I can try to get more questions for you guys. Thank you. From where I get assignment questions? Once again, the assignment questions are so if you access your week one lectures, right towards the end of your week one lectures should be your assignment questions. Okay. Okay, if you guys have no other questions, then I'll thank you, every one of you, for joining. Please join every week so that you guys get comfortable with the course and start to understand what's happening in the field as well. So see you guys next week, I guess. Bye.
So day and time will be same for every week.
Thank you, sir.
Yeah, same day, same time. Tuesday, 7 to
Okay.
8.
Okay.
Unfortunately, I
Thank you,
cannot
sir.
change the time because it's already fixed. But yeah,
Thank you, sir.
Sir,
yeah,
I just have like one small doubt. Sustained and prolonged release are essentially the same thing, yeah, when it comes to.
yeah. They're more or less used interchangeably.
Okay, fine. So there's no like actual distinction between them.
Yeah.
Okay, fine. Thank you.
Thank you.